my name is Mary Lovely S. Trangia, and I will be discussing about prime factors of a factorial notation. Let's begin. Factorial numbers n factorial is equal to 1 times 2 times n grow very fast with n. The prime factors of a factorial number, however, are all relatively small, and the complete factorization of n factorial is quite, air quotes, easy to obtain. We will make use of the following fundamental theorem. So if P divides AB for A prime P, then P divides A or P divides B. So this will be the theorem that we will focus on as we go to our discussion. An application of this theorem to factorial numbers is that if a prime P is a divisor of n, then P must be a divisor of at least one of the numbers from 1 to n. Of course, it would only make sense that if you have n factorial and P, this prime P divides n factorial, then one of the numbers here is divisible by this prime number P. This would immediately imply that every prime factor of n is less than or equal to n. Of course, it can't be greater than n because it's divisible by that prime factor is this one. It divides n factorial. Conversely, every prime number between 2 and n must be a prime factor of n factorial. That's the converse of our theorem. Let us introduce the notation d sub a times b as the number of times that a divides into b. So you have numbers that are divisible by another number, but it could be divisible a lot of times. So this will be the notation that will represent that scenario. Put more precisely, d sub a times b is equal to k if and only if b is divisible by a to the power of k is an integer, while b over a to the power of k plus 1 is not. So this is only possible if these two here are true. We now seek to determine a sub a times n factorial for all primes p is less than or equal to n from Euclid's first theorem and the fundamental theorem of arithmetic, which follows that we have the statement here, d sub p times n factorial is equal to d sub p times 1 plus d sub p times 2 plus until d sub p times n. So let us have an example. Let's take 10 factorial. 10 factorial is equal to 3,628,800. How do we find the prime factors of this 10 factorial here? So let us take p is equal to the first prime number that is in between 2 to 10. N is equal to 10. So let's take 2. First question, how many of the numbers 1, 2 to n are divisible by 2? How do we answer this? So we have this one, the floor function, which is the floor of 10 is equal to 2, which is exactly equal to 5. But that is not the total count because the sum of the numbers from 2 to 10 are divisible by 2 multiple times. So there are some numbers that could be divided by 2 a lot of times. Say for example 8. So you could divide 8 by 2 3 times. 8 divided by 2 is 4. 4 divided by 2 is 2. So you can actually divide 8 a lot of times. So how many numbers are divisible by 2 squared? So you still apply the floor function. So that will be the floor of 10 over 2 squared, which is equal to 10 divided by 4, which is equal to 2 point something and applying the floor function, that will become 2. So therefore, there are two numbers from 2 to 10 that are divisible by 2 squared. How about 2 raised to the power of 3? So still applying the floor function, we have the floor of 10 over 2 cubed, which is equal to 1 point something. Apply the floor function, that is equal to 1. And recall that 10 over 2 is 5, and 10 over 2 squared, the floor of 10 over 2 squared is 2. So how do we write that prime factor? So applying the theorem earlier, we have d sub 2 times 10 factorial is equal to 5, which is from here, plus 2, which is from this one, and plus 1. So that is 8. There are 8 numbers that are divisible by the prime number, 8 numbers from 1 to 10. And that will make the first prime factor of this prime factorial that we have, or this prime factorial that we have, 10 factorial. This is the first prime factor, that is 2 raised to the power of 8. So if you notice, the answer that we got here, that will become your exponent in the first prime factor. So we have 2 raised to the power of 8. But we do not stop there. We need to look for or solve for the other prime numbers in between 2 to n, which is in this case 10. So what's the next prime number? That is 3. So if you have 3, that is still the floor function 10 over 3. So that is 3 point something, or 3. And we could also have 10, the floor of 10 over 3 squared. So that's 10 over 9. So that's 1 point something. If we continue on this, say we have 10 over 3 raised to the power of 3. That is 10 over 27. So 27 is greater than 10. So we have 0 point something. So the answer of the floor of 10 over 3 cubed will be 0. So there's no point. So we just stop on this too. So we have the second prime factor, d sub 3 times 10 factorial is equal to 4, and that would mark as the second prime factor. So we have from earlier 2 raised to the power of 8 times, we have our new answer here, 3 raised to the power of 4. What is the third one? So that is 5, the next factor, prime factor. So we have 10 over 5, which is exactly equal to 2. If we continue on 5 squared, or to 5 squared, that would be 25. So it would be 0, applying the floor function. So d sub 5 times 10 factorial is equal to 2. So we have the third prime factor. So we have 5 squared now. What's next to 5? We have 7. The third prime factor. So that's 10 over 7 is equal to 1 point something, or 1, the floor of 10 over 7. So that's 1. So we have d sub 7 times 10 factorial is equal to 1. So we now have the complete lineup of prime factors that we have, because 7 is the last prime factor from 2 to 10. So these are the prime factors of 10 factorial. We have 2 raised to the power of 8 times 3 raised to the power of 4 times 5 squared times 7. That is it. So we have another way to solve this problem. So we could use this technique. We could write all of the prime factors, but assign variables as their exponents. So for example, this one, 10 factorial, that would be equal to 2 raised to the power of a times 3 raised to the power of b times 5 raised to the power of c times 7 raised to the power of d. How do we find the values of a, b, c, and d? Simply apply the process earlier. So a is equal to the floor of 10 over 2 plus the floor of 10 over 2 squared plus the floor of 10 over 2 cubed, which is equal to 8. B is for the prime factor 3, so that would be the floor of 10 over 3 plus 10, the floor of 10 over 3 squared, which is equal to 4. C would be for 5, so that's the floor of 10 over 5, which is exactly 2. And D is equal to the floor of 10 over 7, which is 1. So substitute the values of A, B, C, and D to the original equation earlier. We would have 10 factorial is equal to 2 times 2 to the power of 8 times 3 to the power of 4 times 5 to the power of 2 times 7. So it's basically more systematic than the one that we had earlier. The first solution that we had. So we could use this one. This is also a solution. Okay. Let's have another example. Say we have 42 factorial, which is a very big number. So this is the answer for 42 factorial. If you notice, it's very long. There are so many digits. And yeah. So applying the concept earlier, the same process. So we could list all of the prime numbers from 2 to 42. So we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, and 41. So we have the exponents here, the variables from A to M. So simply apply the process from earlier. So A would be for the prime number 2. So that's the floor of 42 divided by 2 plus 42, the floor of 42 divided by 2 squared plus 42 divided by 2 cubed plus 42 over the floor of 42 over 2 raised to the power of 5. 2 raised to the power of 6 would be greater than 2 raised to the power of 6 is greater than 42. So that would be insignificant. So that would be equal to 0. So we stop at 2 raised to the power of 5. So if you add all of those here, so we still have 2 raised to the power of 4 in this one. So that would total to 39. So that is 2 raised to the power of 39. For letter B, this is for the prime factor, prime factor 3. Same, that's 42 over 3, 42 over 3 squared, 42 over 3 cubed. So there are 19 numbers from 2 to 42 that are divisible by 19. So you do the same process for the rest of the prime numbers, prime factors, the rest of these ones here, 5, 7, 11, 13, 17, and so on, until you reach the last one, which is M. M is for 41, so that's 10 over, no, that's not 10, that's 42. 42 over 41 is equal to 1 point something, or 1. And then substitute all the values that you got from your solution. So you have the prime factors of a 42 factorial are 2 raised to the power of 39 times 3 raised to the power of 19 times 5 raised to the power of 9 times 7 raised to the power of 6 times 11 raised to the power of 3 times 13 raised to the power of 3 times 17 raised to the power of 2 times 19 raised to the power of 2 times 23 times 29 times 31 times 37 times 41. So if you notice, the exponents on here from 19, or it stopped in 19, 23, and so on, numbers greater than 23, they have the exponents of 1 because we have reached the middle part of 42. 42 divided by 2 is 21, and 21 is less than 23. So the latter half, or the upper half of 42, you don't really have exponents aside from 1. So it's basically you just have to solve for these ones here, the lower half of the prime factors of 42 factorial. Yeah. Alright. So this identity was founded by the French mathematician Adrien Marie Legendre. So she developed this one, this equation here. That's d sub p raised to the power d sub p times n factorial. So this is what we used earlier. So that's the summation of the floor of n over p raised to the power of k as k approaches, as k starts 1 until positive infinity. Alright, so this is her. This is the only known portrait of Adrienne Maria Legendre from 1752 to 1833, which is a caricature by G.L. Boyle. Okay. Notice how the exponents do not increase as the prime numbers increase. This is true in general. Assume that p and q are both primes and p is less than q. Then that would mean that the log of n to the base p is greater than or equal to the log of n to the base q. And n over p raised to the power of k is greater than or equal to n over q raised to the power of k for all the positive integers. If we use this equation, we would get this 1 here. D sub p times n factorial is greater than or equal to d sub q times n factorial for primes p and q, with p is less than q. Thus, that would mean that if you have the prime factors, if we go back to this one, the exponents of the prime factors should be decreasing in order. If you start with the smallest, or in this one 2, so your exponents should be in descending order, so largest until you reach 1. So that's basically what it means. So that ends my report. Thank you so much. If you have questions, feel free to comment down below. Thank you again. This has been very lovely as Trangia. Have a good day or night.